October 2012 in interdisciplinary program in Systems and Control Engineering, Indian Institute of Technology, Bombay, Mumbai, India. His dissertation topic was fractional order modeling of a nuclear reactor with slab geometry. He is a coordinator of this FDP and currently working as HOD of Electronics Department as well as Dean of R&D Department, RAIT. He has several book chapters, patents, and copyrights on his name. He has his papers published in several refereed journals like Journal of Applied Nonlinear Dynamics, International Journal of Dynamics and Control Springer, Annals of Nuclear Energy Elsevier. He has been reviewer for refereed journals. To name a few are Nonlinear Dynamics Springer, Applied Mathematical Modeling, Advances in Mechanical Engineering. He has been Technical Program Committee member, reviewer for international and national conferences. He has several awards in his accolades like Journal Paper Award, Research and Development Award, Best Oral Presentation Award. He has his involvement in several industry-sponsored projects and consultancies. He is one of the members of Board of Studies, Mumbai University. So his today's topic is fractional calculus applications in robotics. So I request sir to start the session, please.
Thank you, Sushma Madam. Hello participants, good afternoon. Welcome to this last session of day 2. Uh, mm, I hope by this time you must have got an idea of what we have planned for you in this FDP. Okay, so we are focusing on the research contents and what are the probable research avenues available for any faculty member or a researcher in the area of robotics. So in this in continuation to this, I'll be presenting today's talk on fractional calculus applications in robotics. So it will be a slightly digression from what you have been watching from yesterday. If we take a quick review of yesterday and today, we started with Mr. Lentin Joseph's lecture on ROS, Robot Operating Systems, followed by 2 laboratory sessions by Ajit on ROS. Okay, and then today morning, Dr. Leena Vachani from Systems and Control IIT Bombay, she presented the embedded systems usage in robotics, especially multi-agent systems and other types of robotic systems. Then we had today afternoon before this session, Dr. Soumyaranjan Sahu from IIT Kanpur, and he gave an example of UAV, and he showed both the theoretical work done by his team as well as the experimentation or experimental validation of this. Okay, so what I am going to cover today, or what I plan to introduce you to all, is an altogether new field which can be used for modeling and control. In general, modeling and control, but since our scope is limited to robotics, we will talk about the use of new mathematical tool which is known as fractional calculus, okay, in modeling and control of robotic systems, and what are the various research avenues available in this field. Okay, I think some of you might have heard about this new area, not a quite new area, about fractional calculus. Okay, so as the word suggests, as the terminology suggests, it's a calculus. Okay, we all are aware about our conventional calculus, derivatives and integrals. Now, every time when we take the derivative of a function, okay, so now let me share my screen, okay, and let me try to tell you about this. Okay, just a moment. Some okay, just a moment. Just am I audible?
Yes, sir.
Yeah, okay. Is my screen visible?
Yes, sir. Your whiteboard is visible.
Okay, fine. Thank you. Okay. So our topic basically is fractional calculus applications in robotics. Okay, right. Now, fine. So this involves basically two terms. One is fractional calculus, okay, and the another term is modeling and control of robots. Okay. Now, what is this fractional calculus? Okay, I have a presentation for this, but I will try to explain to you. Okay, so we all know this differential and integral calculus. Okay, so in this we know how to take the derivative. Okay, we know how to do the integration. Okay, the main point here is this derivative and integration is always of integer order. What does this mean? This means that if I am I am given a function f of t. Okay, I will be taking its first derivative, then I will be taking its second derivative, then I will be taking its third derivative, and so on. Okay, so this we can denote it as, given f of t, it is d square f of t, where capital T represents basically this derivative order. Okay, similarly in case of the integration.
Sir,
Okay,
sir, sorry,
yeah,
your sir,
yeah.
whiteboard is not completely visible.
No, I have
Like,
just moved it.
huh, sir?
I have moved it. Is it visible?
No, sir.
Whiteboard is not visible.
Yes, sir.
Oh, okay, let me share again.
ते whiteboardचं ऍप करून करतात आयकाच्या स्क्रीनवरती वेळ होतो डिस्प्ले ते ऍपमध्ये जाऊन
Is it visible now?
Yes, sir.
Okay, fine. Okay. So we talk about this first order derivative, second order derivative, and all that. Okay. Similarly, if I am given a function, okay, right, I will integrate it once, I will integrate it twice, I will integrate it 3 times, and so on. Okay.
Sir,
Likewise, I
sir,
can
sorry, sir.
integrate.
Sorry, sir, to disturb you.
Yeah.
The participants mostly they are not able to see the screen.
Okay.
It is not visible. Whatever you are writing down, it is not visible, sir.
Okay. 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 Just give me. Okay. Fine. I'll stop using whiteboard. Maybe I'll directly jump to the uh, presentation. Okay, fine. Is my presentation visible?
Yes, sir.
Okay, fine. Thank you. Then I'll go with this presentation directly. Okay. I hope I have made it full screen. It is visible.
Yes, sir, fully visible.
Okay, fine. So basically, what I was going to tell you through whiteboard was that this d by dt is used to represent rate of change. Okay, geometrically it means slope of a tangent. Okay, integration is nothing but continuous summation. It is interpreted as area under the curve. Okay, and this conventional integer order derivative and integer order integration, where the derivative order or the multiples of integrals are always integers. Like derivative, we will always take first derivative, second derivative, third derivative. Okay, integration is you have a function, you integrate it once, you integrate it twice, you integrate it thrice, and so on. So you go on integrating. Okay, but does this question come to our mind that why the derivative order always has to be an integer? Why the derivative order has to be always 1, 2, 3? Why I cannot differentiate or integrate a function? Or if we talk about derivative, why can't I differentiate the function? Okay, with the derivative order as 0.5. So imagine you are given a function t square ramp function, and you are asked to take its first derivative. The answer is very simple. The first derivative of t square is 2t. Okay, its second derivative is 2, and its third derivative is 0. Okay, the question that arises is, what will be the result if I differentiate t square with a derivative order 0.5, or a derivative order of 0.3, or a derivative order of 1.27, or a derivative order of say 0.66, or maybe 1 by pi or 1 by e, and all those things. Okay, so that question is very interesting. Same is the case with integration. You have a function, you integrate it once, you integrate it twice, thrice, and so many times. Okay, It is like you are passing a signal through a chain of integrators. Okay. Now the question that arises is, okay, if you do it, why always you have to have after first integration, you should have a second integration. Why can't the integration order be also 1.5 and 1.2 and all those things? Okay. So this conventional calculus where the derivative order is always 1 and 2 or integers is known as integer order calculus or the conventional calculus. Okay. And it has been very successful in modeling various systems, and robotic systems are also no exception to that. If you open any book on robotics, okay, maybe Clafter, Fu or any textbook or any paper, okay, you will find that this conventional calculus is being used successfully, okay, for modeling a robotic system, maybe a robotic arm, maybe a manipulator, maybe a robotic bird, or maybe a multi-agent system or whatever it is. Okay, so it has been used for modeling such robotic systems and other general systems also. I have given here some examples like RLC circuit, spring mass damper system and all those things, Maxwell's equation and everything. Okay, the question that arises is, okay, can I have a better mathematical tool which can be used for modeling the real world systems? And since we are in the purview of robotic systems, okay, can I use this calculus where the orders of integrations and derivatives are non-integers? Can I use them for modeling robotic systems? Can I use them for controlling robotic systems? Okay, first question. But then comes the question of motivation. Okay, is it really helpful? Okay, if I use this mathematics, this new mathematical tool, will there be any improvement in my mathematical modeling of a robotic system? Will I achieve a more precision control or a better control? Okay, if I use a fractional order PID controller for that, because the simple PID involves proportional, integral and derivative. So there is an integration and derivative coming. In the conventional case, it's the integration and derivative of the error signal, which is obtained as the difference of your set point and actual output. Okay. So now this question is coming to our mind is, can I use this advanced mathematical tool, okay, for modeling robotic systems? So why the order should be always 1, 2, 3? Okay, the fractional calculus, as it is commonly known as, okay, we wish to have half order, pith order, or even half order means rational order, pith order means non-rational, irrational number, and even complex number. Okay, complex order derivative, okay, of a function. So we are talking about specifically such type of functions. Okay, so my lecture would be such that initial half an hour I would be spending on to give you a glimpse of what is this fractional calculus. Okay, and I'll also be presenting a couple of examples, real world examples where this fractional calculus has given better mathematical models. Okay, and even fractional order control also. And then we will switch over to, I'll show you some literature survey. Okay, because the title of my talk is fractional calculus applications, okay, in robotic systems or in robotics. Okay, right. So if you have understood this, then the fractional calculus is defined as derivatives and integrals of arbitrary, real or complex order. Okay, so please read this definition carefully. Derivatives and integrals, okay, where the order is real or complex. Okay, right. So these questions would obviously come to your mind. Those who are being introduced to this topic for the first time, I hope now it is known to majority of the researchers. Okay, so the first question is, does it make any sense, or is it just a mathematical fantasy? Define it. Tell me how to calculate half order derivative of a ramp function f of t equal to t. This seems to be a recent stuff. How old is it? How much serious is the research community about it? This is the question on which we are going to ponder a lot, and we are going to have a look at it. Maybe last 45 minutes of my talk, I will be showing you number of papers which I have downloaded, okay, and which talk about this this applications of fractional calculus. Okay, does it have any physical interpretation and geometrical meaning? Okay, why study it? How is it important in engineering and in robotics? What's the deal? What are its applications? And so should we discard the integer order derivatives? Okay, so these are some of the questions that we will try to answer. Initial 3-4 questions are related to theoretical stuff, but the last 4-5 questions are we will orient it towards our theme of the FDP, that is robotics. Okay. So let me give you a quick glimpse of the history of fractional calculus. It is as old as classical conventional integer order calculus, born in 1695. Born in the sense that this idea was first discussed between L'Hopital and Leibniz. Okay, at the end of 17th century. So you know that this integer order calculus or the conventional calculus, okay, was brought both by Newton and Leibniz. They were contemporary, and both simultaneously around they floated this idea. Okay, and it was a sensation in the mathematicians in the Europe at that time. And this L'Hopital, being a mathematician, he wrote a letter to Leibniz asking the question, what if the derivative order is 1/2? Okay, so see, in 1695, L'Hopital had this question in his mind. Okay, isn't it very interesting that we all went through this 10+2 and engineering curriculum, but never this question came to our mind? And for an engineer, being of any branch, the derivatives and I mean differential and integral calculus is like a daily bread and butter. So, but this question never come to our mind. Why the derivative order always has to be an integer? Okay. So Leibniz gave a very prophetical reply to this. He said that he gave answer in the terminology at that time, which was used at that time. But then he made a very prophetical statement. He said that from this one day useful consequences will be drawn. Okay. So he said that right now I am not able to give you a clear-cut idea. It looks very paradoxical to me because calculus rules came because people needed some mathematical framework to for Newton's laws of motion, basically to give a mathematical framework to Newton's laws of motion, basically. Okay, so he couldn't understand this half-order derivative concept. Rather, he failed to give any correct answer for that. But he said that I think in future it would be very useful and people would be able to draw useful consequences. And this letter of Leibniz was on 30th September 1695. So 30th September is considered as the birthday of fractional calculus. These are some of the contributors in our mathematical tool, fractional calculus. So Leibniz, Euler, Lagrange, Laplace, Fourier, Abel, Liouville, Riemann, each one of them is a stalwart, and they have made very fundamental contributions to this field. Acceptance by research community, there are more than 50 books. 50 is also a small number now. I can say there are more than 100 books. There are dedicated international journals. First conference took place in 1974. An International Federation of Automatic Control organizes every 2 years a dedicated symposium. I would call it as a symposium on fractional differentiation and applications, and you will find, I mean, tons of papers people are now publishing on applications of fractional calculus in any field. Okay, these are some of the Indians who are working in this area. Okay, so they are spread across the country, and if you see the latest Google Scholar profiles and Scopus and all that, you will find that more and more number of people are joining this community and they are publishing papers. Okay. Some facts about fractional calculus. Okay, so it's a rigorous mathematical theory has been developed. Integer order calculus is a special case because the moment you talk about, I mean, I'm really feeling very sorry. Had my electronic pad been working, I would have given you wonderful interpretation for this. Okay. So there is a rigorous mathematical theory developed, because the moment you talk about integer order, you generalize the idea of integer order derivatives to a fractional order derivative. All those questions come in, continuity and all those things, and then how do you implement it on an embedded system? How do you do its approximation? How do you simulate it? And all those things. Okay, so all those have been taken care of. And the last thing is very important. There are more than 30 definitions of fractional derivative operators. Okay, so in conventional calculus, uh, the only definition that is available is basically, let me see if I can, let me attempt again one more time my, because
Sir, the app not open.
okay, just a moment. Just a moment. Okay. Okay, just give me a moment. I'm sorry for this interruption, but there is no beauty if we teach it on a presentation. There is no fun. Okay.
Desktop share.
So by the time it gets loaded, okay. Yeah, is my whiteboard visible now? Sushma madam?
Yes, sir, it's visible.
Okay, so now let me give you. So you are talking about. So you are talking about this f of t, and you are talking about its d by dt. Okay, right. We want to generalize it to f of t. Okay, and the derivative order is alpha. Okay, right. So so this is how we have to do it, and now I am going to tell you. So the moment you talk about this fractional order derivative, okay. So the moment you talk about this fractional order derivative, okay. How do I move down? Okay. Okay. Fine. So there are yeah. Okay, right. So you need to basically understand that since we are talking about this fraction, so if this is f of t, okay, right, and it is and if I write this f of t as t square, okay, so you have t square and you take its d by dt, you get 2t. Okay, but the moment you make it alpha order derivative, the question that comes is what will be this fractional order derivative and how do I calculate it? Okay, and therefore what happens is when you are going ahead with this particular mathematical tool, then you need to basically understand that in the conventional case, okay, if you are taking the fractional derivative or if you are taking the integer order derivative of a function, okay, so you have this very simple definition. So you have f at t plus h minus f of t divided by h. Okay, this is how you calculate the conventional derivative of a function. What does it mean graphically? Graphically, it means that this is t, this is f of t, okay, right? Okay, and you have this function f of t, okay, right? Now this is your t, this is your t plus h, this is your f of t, and this is your f of t plus h. Okay, so you basically calculate the difference between these two and divide it by this h. This is your h. To divide it by h. Okay, this is how you calculate the derivative. The moment you go with a fractional order derivative, I will not go into much of mathematics. The moment you take f of t and you calculate its fractional order derivative, okay, what does it mean is that it is f of t plus h minus f of t, okay, whole to the power alpha upon h to the power alpha. Okay, and when you try to basically calculate this this numerator, okay, it results into something which involves f of t plus h, okay, it involves f of t, then it involves f of t minus h, f of t minus 2h, and all these things up to f of 0. Okay, fine. Huh. ठीक है, okay, right. So this is how you do it. Now what happens is in case of conventional derivative, you take f of t plus h, f of t, and you divide it by h and you get your derivative. Okay, but in case of fractional derivative, when you are calculating the fractional derivative of the function, okay, assuming that this function starts from t equal to 0, okay, to calculate the fractional derivative d alpha of f of t, to calculate the derivative of this alpha of this f of t at t is equal to t plus h, when you want to calculate this derivative, you need this complete history of the function. You need this complete history of the function. What does this mean? This means that integer order derivatives, okay, are local operators, because to calculate integer order derivatives you need only this value and this value, but when you talk about fractional order derivatives, okay, it's a non-local operator. What is the meaning of this non-local operator? Here for local operator you need f of t plus h and f of t. Okay, in this case, in this particular case, when you are calculating fractional order derivative of a function, okay, all values of f of t from t is equal to 0 to t is equal to h. All these values are required. So what difference does it make? I could have explained all this with the help of a PPT, but then you would not get the feel for this question. Okay, for this point. So what does this mean? This means that in this case, this particular system or this particular mathematical derivative, fractional derivative, okay, considers the memory of the system or memory of the function, okay, and therefore it can be used for modeling systems with memory. This is very important. What I have written here is very important, that fractional order derivatives can be used for modeling systems with memory. Okay. In other words, what does it mean? So it means that if a physical system has, number one, memory, okay, or distributed dynamics, or if it has some flexible structure, okay, because flexible structure has got these distributed dynamics. For example, if you take a rigid rod, okay, if you take a rigid rod, okay, right, this rod, you can lump all the dynamics of this at one point, okay, we call it as center of gravity, right? You can lump everything at one point and this can be used as a mass, some mass m, okay, but the moment it has got some flexible structure or flexible characteristics, okay, right, then you need to consider this distributed dynamics, okay, for modeling such systems, okay, because it has got distributed dynamics, and our fractional calculus says that it can be used for modeling such flexible manipulators, you can say, in case of robotic systems, or it can be used for modeling flexible robot arms. Okay, so this is very important, and this particular feature, so this property, okay, of fractional calculus. When I talk about fractional calculus, I am talking about fractional derivative and fractional integration, okay, has been useful in modeling robotic systems. So manipulators, then you talk about multi-agent systems, okay, and all those things. It has been used for that. I am going to show you the literature survey. I am going to show you some of the papers. Before that, let me give you an example, okay, like you have a, you know that robotic manipulator, for robotic manipulator, okay, right, we need this spring mass damper system, okay. What is this spring mass damper system? Okay, so you have a spring, okay, you have a damper, and you have a mass, and here somewhere, so this is mass, okay, this is spring, and this is your damper, okay, and you apply some force here, Okay. Now, if you look at any robotic modeling, manipulator modeling text, okay, you will find that this approximation has been used, or this analogy of spring mass damper system has been used, okay, for modeling a robotic manipulator or some part of the robotic manipulator. It's an essential part of a robotic manipulator modeling. Okay, so you basically represent the dynamics like this. Now, if you want to go for the mathematical model, how do you define the mathematical model? M this, and your x of t is your displacement. Okay, you also have a displacement here, x of t, m d square x by dt square plus f dx by dt plus k into x is equal to f. Okay, this is how you use the spring mass damper system modeling. Very simple. Spring mass damper system being used for simplifying a robotic manipulator or some of its subsystems, and you use this basic model. Now here the question comes is this f. We will talk about this f basically. Okay, this f. Okay, this f is a damper element. Okay, right. So it has got some viscosity. Okay, it has got some viscosity. Now what if this f has got viscosity as well as elasticity, both? Okay, so these two terms are combined together, and that is known as viscoelastic. It is a viscoelastic material. Okay, so this spring mass damper system I am talking about, it is a viscoelastic material. Okay, now if you want to model such system, okay, where there is a and in majority of the cases it is indeed a it shows viscoelastic dynamics. Okay, but for assumption we ignore that, we assume this only as a viscous thing, right? And if we assume this as a viscoelastic thing, then the question that arises is, I can no longer represent its mathematical model using this dx by dt. Okay, I cannot model its dynamics using dx by dt. If I use it, okay, if I use integer order derivative, if I use this integer order derivative, okay, the model does not capture the dynamics of the damper element. Okay, it does not capture faithfully, I should say. It does not capture faithfully the dynamics of the damper element. So what is to be done in this case? Then what we do is basically we replace this by a fractional derivative. Okay, f d alpha by dt alpha of x of t. This is how we replace the integer order derivative in the above differential equation. Okay, the moment we make it, okay, the moment we make it, and what is the advantage of this? The advantage of this is that it gives me a more faithful model. So this is a more faithful model. This is a more faithful model. Okay, right. And therefore there are a lot of papers available which talk about replacing the damper model from integer order derivative to fractional order derivative. Lot of such models are available. Okay, and lot of such papers are also available which have experimentally proved that if you use this, then you get a better model. Fine. Now, the moment we do this, okay, we come across a model which is a fractional order model. So I'll replace this by fractional derivative where alpha, yeah, I forgot to tell you, this alpha is a real number, positive real number. Alpha is a positive real number. So you can have alpha is equal to 0.5 or 0.2 or whatever it is. Okay, right. So you can use this and you can come up with a fractional. So the moment you do this, it becomes a fractional order model. It becomes a fractional order model. Okay. So this is how we can use fractional derivatives for modeling. So we have seen up to this point that fractional derivative is you have a function f of t and you take its fractional order derivative, okay, used for modeling systems with memory, okay, spatial dynamics, okay, and viscoelastic structures. Okay, let's have a discussion on this spatial dynamics. Okay, in control systems terminology, they are known as distributed parameter systems. Okay, let's take an example of this. Um, let's take an example of this a swarm of robots. Okay, you have one robot here, you have another robot here, you have another robot here, you have this multi-agent system, something like this. Okay, now the XY coordinates, let's talk in the 2D plane. The XYZ, you can say the XYZ coordinates will play an important role here. Okay, right. So it has been shown that if you have a such distributed parameter system, then your fractional derivatives give you a very good understanding, okay, and the model that you develop is more faithful as compared to the integer order derivative. Okay, right. Any questions up to this point? We can take couple of questions if they are there. So I have not deliberately gone into the mathematics. I have not gone into the, I can share my presentation. I will share my presentation with all of you. Okay. So mathematics I have not considered. I have just told you that replace d by dt by d alpha by dt alpha, and the moment you do it, okay, this derivative is local. Local means if you want to calculate this derivative at say t is equal to 3 seconds, you need the value of the signal or function at t equal to 3 seconds and then the one sample behind that, back of that, and then you just take a difference, backward difference rule, divide by the sampling time, you get your derivative. In case you are calculating fractional order derivative, okay, right, you need the complete history. Complete history is required for that. We can take questions, couple of questions if they are there, because then next I will move to fractional order control and then we will actually have a look at some of the research papers. Yeah.
Dear participants, you can raise your hand or you can type the question in the chat box.
So if there are no questions, we'll move ahead. Shall we move ahead?
Sir, no questions, sir.
Okay, fine. No issues. Fine. Next, we talk about FO control. So I'll give you a very simple example. PID, integral derivative. Okay. So this is proportional. Proportional we are not interested in. Okay. Now the moment I talk about integral, okay, can I replace it with a fractional integral? Can I replace it with a fractional derivative? Okay, and the moment I talk about this, I will have pi to the power alpha d to the power beta. This is my fractional PID. Okay, what is so interesting about it? The interesting about it, let me draw a block diagram, simple block diagram, control system block diagram. So here is your reference signal R of t. Here you have your output Y of t. Here is your, this is your plus, this is minus. Here you get your E of t. Okay, you have a PID here. PID is very popularly used in, this is your plant. Okay, or I would replace it by G. Okay, so you have G here, your plant. Okay, and this is your feedback. Okay, this is your Y of t. This is your U of t. Okay, right. So you have such thing. Now here, when you talk about a conventional PID, okay, the parameters that you have to tune, okay, are, in case of conventional PID, you have to tune Kp, Ki and Kd. These are the three gains that you have to tune. Okay, but the moment you talk about a fractional PID, okay, you have 5 parameters. Okay, so here you have Kp, Ki and Kd. In addition to that, you have alpha and beta. Alpha is your integration order, beta is your derivative order. Okay, what is the advantage of this? Advantage is that more maneuverability. Fine control. Okay. More closed loop robustness. Okay. Less control efforts. This is known as cheap control. So you spend less energy. Okay. Your control system is, from energy point of view, is cheaper, less control. Okay, right. So the moment you replace your integer order PID by a fractional order PID, okay, I'm giving you one simple example, right? You get all these advantages. So instead of this PID here, it will be fractional order PID which is present, and again alpha and beta are your real numbers, positive real numbers. Okay, right, and you can use for controlling this. Okay, so I hope this also is very straightforward. I have not deliberately gone into the mathematics of fractional calculus. Okay, and I have avoided that. That's why I was keen to use the whiteboard, so that I would be able to give you an idea, because presentation would be like very dry and there will be a lot of mathematics involved in that. We will not go into that details. Okay, now if you look at a robotic system, okay, so now let's come to robotic system. Okay, when you want to design, okay, a robotic system, basically you have to do modeling. Okay, then you have to do the controlling. Okay. Third one it's hardware implementation. Okay, right. So therefore, in this case, in all the three cases, okay, fractional calculus has been successfully used. Okay, for this. The question you may ask is how to do simulation and how to do hardware implementation, all that. Because when you, the moment you talk about today, Leena madam, Dr. Leena madam told you about implementation. So you may have a microcontroller, you may have a DSP processor, you may have an FPGA, or you may have some HIL, okay, anything you may have, right? So you can successfully implement your fractional order controllers, okay, on these hardware platforms. Okay, so what is the takeaway? Takeaway is that, I'll just summarize the takeaway. The takeaway is that if fractional calculus is used in robotic systems, you get better, more faithful model of the robotic system. Okay, right? Better, more precise, efficient control of robotic system. Okay, and the third thing that is very important is straightforward implementation on hardware platform. Okay, so these are the, this is what in a nutshell you can talk about. This is the takeaway from this talk. This is the takeaway from this talk, that if you use fractional calculus for this, okay, then you can get better or more faithful model of the robotic system. Okay, better, precise, efficient control of robotic system. Okay, and straightforward implementation on hardware platform. Okay, do we have any questions up to this point, or I'll move ahead with the with showing the papers? Moderators, are there any questions?
No, sir.
Okay, fine. Now I'll just share with you the some of the papers, okay, that I thought would be useful to all. Okay, I'll stop this sharing and I'll share a new thing. So each time I have to share a new paper. Okay, fine. Okay, fine. Just a moment. I'll keep all these papers open. Okay, just give me a moment. Okay. So I am ready. Okay, is my screen visible?
Yes, sir.
Okay, fine. So this is the presentation that I was talking about, but I'll not share it. It's quite mathematical. Okay, so let's have a look at this first paper. Okay, it talks about analysis of fractional order robot axis dynamics. What I'm doing right now is I introduce you to the basic theory, not even basic theory. I just gave you a glimpse of what is fractional calculus. So fractional calculus involves fractional order derivative and fractional order integration. If you talk in terms of engineering applications, you can broadly divide fractional calculus applications into two parts: fractional order modeling and fractional order control. Okay, and then I gave you an idea about how to do a fractional order modeling, a very brief idea, and how you take care of fractional order control, and what are the advantages of using fractional order modeling and fractional order control for robotic systems. Now what I am going to show you is what selected research people have done in this area. Okay, and we will also summarize what are the research avenues available in this particular field. Okay, because the theme of our workshop, our FDP, is emerging research trends. Okay, so what are the various research avenues available? What are the problems which have got good research potential? Okay, so look at this paper which talks about analysis of fractional order robot, the transfer function model for this. Okay, and then it was then fractional derivative was used for basically modeling it. Okay, right. So this is a I think this is a conference publication, but it will give you, I can share all these papers, or you yourself can find this also on on this. Okay, right. Next paper is the fractional nonlinear robotic manipulator modeling and dynamic simulations. Okay, right. So here you will see, I'll just read this. I'll zoom it first. Okay. In this paper, we applied the Riemann-Liouville approach and the fractional Euler-Lagrange equations in order to obtain fractional order nonlinear dynamics equations of a two-link robotic manipulator. Okay, right. So a two-link robotic manipulator has been considered. Okay, and its nonlinear dynamics has been represented by fractional derivatives or fractional calculus. Okay, so let's have a look at this. So these are the basics of this fractional calculus and all that. Okay, so here you can see these definitions. Okay, you can see this definition where this is your f of x function. Okay, and this is d to the power nu. Nu is your fractional derivative order. Okay, right. So then they use this Euler-Lagrangian framework for modeling, and this is a simple two-link planar manipulator. Okay, and they have this is the integer order model. Okay, and then they have got a fractional order model for this. So this you can say in the Euler-Lagrangian setup, these are the integer order models, means conventional models. Okay, right? And then they have got a fractional order model, and the derivative order is considered as 5 different derivative orders: 0.4, 0.6, 0.9, 1.1 and 1.2. Okay, and they have got the results. Okay, so they have plotted, since it's a nonlinear dynamics involving system. Okay, They have got it as a chaotic system. Okay, and they have shown this. Okay. So here is an interesting observation which is given in this paper. It was observed that as alpha approaches 1, okay, phase diagrams converge to those obtained by integer order modeling. Okay, right. So very interesting that this shows one important thing, that our integer order calculus or our integer order models are a special case of fractional order models or fractional order derivatives, where the derivative order is equal to 1. Okay, right. I hope this is clear. Then we go for the third paper, which is on fractional order mathematical model of pneumatic muscle drive for robotic applications. Okay, this is a book chapter. So let's have a look at the abstract. What does it say? Okay. Okay, so we will go ahead. So this is a single robotic joint, and they have used mathematical model to derive it. Okay, to get its model basically, and then they have introduced fractional order derivatives, and finally they have introduced the fractional order model for this. Okay, so here you can see, you can see the transfer function. Okay, it is 1 upon C2 s to the power V2 plus C1 s to the power V1 plus 1, where V2 and V1 are non-integers. In conventional case, it would be a second order manipulator model. It will be C2 s square plus C1 s plus 1. Okay, but now here, this is, they have used fractional dynamics. They have got a fractional order model for this. Okay, and here they do some kind of comparison. Okay, so you will see that they have got actual measured response. Okay, and then the simulated fractional order system response. Okay, so they considered some fractional derivative orders for their model, some value of nu1 and nu2 in the transfer function that we saw. Okay, and they simulated it, and they found out that, okay, the fractional order system response is more closer to the measured response as compared to the fourth order system. This is very interesting. So you have got an actual measured response from obtained from experiments. Okay, then you have an integer order model. The integer order model is fourth order. That means there are 4 states involved in that. Okay, and then you go for a fractional order model, and it has been found that the response of the fractional order model is much closer to the measured response as compared to the integer order fourth order system. Okay, this is the main takeaway from this. Okay, so you can see they have got the errors here. Okay, so you can see the errors in case of fractional order systems are very less as compared to the errors that are obtained when an integer order model is used. Okay, let me give you an example. Let me show you the next thing. Now this is very interesting, that there has been a dedicated book in Springer, okay, which is on fractional order modeling, fractional modeling and controller design for robotic manipulators, and it is written by one of my friends, Abhay Pal Singh. Okay, he works in the Symbiosis Institute of Technology. He is one of the co-authors. Okay, and they have also done the hardware validation for this. Okay, so very interesting. Now people have started writing dedicated monographs. Okay, for applications of fractional calculus in controller design, modeling and controller design for this. So let's quickly have a look at the index. Okay, contents part of this. Okay, so you see it introduces fractional calculus. Then this talks about a fractional order modeling of robotic systems. And as I said, it starts with a mass spring damper system, the one that I showed you all on the whiteboard. Okay, so let's have a look at this. So spring mass damper system. Okay, so you have this spring mass damper system, right? And you have got a integer order model for this, and then you talk about a fractional order model for this. Okay, this is also one type of a system which is inverted pendulum. Okay, so let's have a look at the index again. Okay, right. So fractional order modeling of this system. Okay, so let's have a look at this. Okay, so so embedding to inverted pendulum on cart. Okay, so they have got this fractional order model for this. It's a multi-input, multi-output system basically. So you have got these two models, and you can see here, if you look at equation number 2.75, you will find your Laplace variable s in the transfer function has got powers as 2 alpha and 4 alpha, where alpha is between 0 and 1. Okay, right. So this is what it is. 2D gantry crane system. Okay, here also they have given the MATLAB code also. Here also you have got this fractional order model for that. Embedding to missile launching vehicle. Okay, so here also they have got fractional order models for that. Okay, so it's very interesting that there are a lot of people and lot of researchers who are moving towards using fractional calculus as an effective mathematical tool for both modeling and control of robotic systems. Next chapter is about FOPID controller. Okay, right. So before that, I'll go to this next last paper that I'm going to show you, okay, which talks about complex order dynamics in hexapod locomotion. Now people have not stopped up to the fractional derivatives. That means derivative with the order as a non-integer 0.5, 1.2, 2.3 and all those things. People have even moved ahead. Researchers have gone beyond that, and now they are talking about fractional derivative or derivatives where the order is a complex number. Okay, so let me quickly tell you about this. Okay, okay, so okay, so people are, is my whiteboard visible? Is my whiteboard visible?
Yes, sir.
Okay, thank you. Okay, so people are basically now talking about, okay, people are talking about, so we had this function f of t. Okay, we had this function f of t. We talked about d by dt of f of t. Then we move to d alpha by dt alpha of f of t. Okay, now people have moved ahead and they are talking about the function with the derivative order as alpha plus j beta, alpha plus j beta. So this is known as, this last one is known as complex order derivative, where the order is a complex number. People have even moved ahead. People have even talked about a function f of t where the derivative order is another function g of t. Okay, so I can give you one example. You have sin t and its derivative is of order cos t, like this. This is known as variable order derivative. Variable order derivative. Okay, so what I was talking about is this complex order dynamics. Okay, so hexapod locomotion. Hexapod is a robotic system basically in its locomotion, and this paper has been published in Elsevier Signal Processing, so very reputed journal. I think its impact factor is more than 2 at least. Okay, so in this paper studies the dynamics of foot ground interaction in hexapod locomotion system. Okay, right. So they have used so you see, for that objective the robot motion is characterized in terms of several locomotion variables, and the ground is modeled through a non-linear spring dashpot, that is spring mass damper. Dashpot means nothing but damper. Okay, system, right. So you will see here that they have used, this is this hexapod. Okay, its movement, it's a robotic system, hexapod robot model. Okay, they have got the mathematical model for this. Okay, and using this model, okay, they have gone one step ahead, and they have got the complex order model for that. Okay, and they have got the answer, and they have got the simulation results and the analysis that they have presented for this. So you can see alpha x1, beta x1, alpha x2, beta x2. These are alpha and beta are nothing but your orders, the complex orders. Okay, right. So you see, you can read this particular thing. Replace s to the power alpha plus j beta by something more complicated and all those things. Okay, right. So now this is as far as control is concerned. So modeling, FOPID controller, now controller we will talk about. Modeling we saw. Okay, so in this I am coming back to this book again. Okay, so you have got a simple spring mass damper system. Okay, and you design a controller for this, right. This is the output of PID controller. This is your conventional PID. Okay, then you talk about FOPID controller, and this is your FOPID controller. Is, as I said, there is alpha k upon ki upon s to the power alpha is fractional integration, and s to the power beta is your fractional derivative. Okay, so both are designed, and you find the response here. You can have a look at. I'll just zoom out slightly. Okay, you can find the response. You can see that PID controller response is with black dashed one, and FOPID is with the blue one. You can see the FOPID. What you see here is, okay, the FOPID, with FOPID controller, the closed loop response settles faster. Okay, earlier it settles to the steady state value as compared to your IOPID or the conventional PID. So this is what I would like to show you. I'll just open a couple of more papers also. Okay, just give me a moment. Okay, so I think this paper is also visible. So this is fractional control of a humanoid robot reduced model with model disturbances. When Dr. Soumya presented, I had asked him one query: how do you take care of the disturbances? Okay, and to make sure that your closed loop robotic system is not affected much by the external uh, disturbances on which you don't have as such any control. okay, right, of course, within a bound, okay, right, then you need to make your closed loop system more robust. Then your controller has to be robust, and we saw that the fractional order controllers are more robust. They make the closed loop system more robust. So this is published in Taylor and Francis journal, okay, right, and they have used this fractional. So you can see this humanoid robot, okay, and they have taken its abstract mathematical modeling using a triple pendulum equations, okay, and they have used so implementation of fractional order controller. They have designed the fractional order controller, okay, right, and it has been done using MATLAB. Okay, so MATLAB has been used. Dr. Prasid is going to take some back-to-back sessions, I think tomorrow or the day after tomorrow, on using the robotic toolbox of MATLAB. Okay, right. So you see, you get a smooth trajectory the moment you use fractional order control for this. Okay, I think I can stop here now. It's almost 4:40. Okay, I'll stop sharing my screen, and we will take some questions if they are there. Okay. Uh,
Sir, one question is there in the chat box.
yeah.
S. Khandekar sir has asked that what are monograms?
What are
Monograms.
monograph? Okay.
Monograms. Yeah.
No, I didn't use any word like monogram. I used a word called monograph. Monographs
Yes.
is a specialized book, okay, which is focused to one particular area. Like the book that you saw, okay, it focused on just one area, okay, of fractional order modeling and control. So I hope he intends to ask that question. Okay. Next
Okay,
one.
sir. That's it, sir. Any other
Okay.
questions?
Please feel free to ask the question. So what I would like to tell you is that all participants is that this is an open area. It has got a lot of potential for publishing papers and doing good research. Okay, so do consider this area combining fractional calculus and robotic systems using for both modeling and control. Okay, we can stop now. Yeah.
Okay.
We'll meet tomorrow at 11.
Yeah. So one participant has written that it is a new era of research and thanks for exploring it.
Yeah, thank you, thank you.
Okay. Okay. Thank you, sir, for explaining fractional calculus in detail. I hope all dear participants can make use of these concepts for any interdisciplinary areas like robotics and for more precise results. So I thank you, sir, for delivering such a nice session.
Thank you.
Thank you, sir. Thank you, sir.
Any instructions to participants?
Uh, we are we are having a session tomorrow at 11 o'clock by Dr. Birazar sir, and he'll be enlightening us for the topic artificial vision for robots. So I request all the participants to be there at sharp 11 o'clock.